So I think we try to catch up the time a little bit. So without further delay, I'm going to introduce our next speaker, Keller. Sharon has worked as a computer scientist for the U.S. federal government since 1983. And she joined the NIST Computer Security Division in 1988. She is the director of the NIST Cryptographic Algorithm Validation Program. She has designed and developed the CAVS tool. And for all the labs that we are here, we know this tool by heart. We use it so often. That is the tool that we use for the algorithm testing. Sharon is going to talk about the CAVP inside the world of the cryptographic algorithm validation testing here. And Sharon, the floor is yours. Let's give a warm welcome. Oh, okay. Sorry, I need to get the slides up for you. Close this one. And it's here. This one is yours. You use PPT? Should be. Okay. I don't know why there's two. So that's yours, huh? Yeah, good. Okay. Melanie, thanks for the introduction. Basically, I'm going to just give a pretty thorough overview of the whole CAVP program so that you get an insight into like a whole bunch of the different facets of the whole program. To begin, it's always good to start with a mission, and our mission is to provide federal agencies in the United States and Canada with assurance that a cryptographic algorithm implementation does adhere to the specifications in the applicable standards. So that's always been our mission, and so it's good. As Randy said, the CAVP used to be within the CMVP because we only had 3 algorithms, and it was just getting off and didn't, and it started to grow and realize how many algorithms there were going to be. So in 2003, we split from the CMVP, and the cryptographic algorithm validations are a prerequisite to the cryptographic module validations. To just show you the flow of how things work, the cryptographic technology group at NIST those people are the ones that determine which cryptographic algorithms become recommendations and standards. And I know that there's a whole process and they work with other people, but that's not the focus of this talk, okay? They analyze the algorithms, they finalize the specifications, and that's what gets put out there in your special pubs and in your FIP standards, which tells us exactly how this algorithm needs to be implemented in order for it to be secure. The CAVP then takes that standard, becomes very familiar with everything in it, and develops the validation test suites for the approved cryptographic algorithms and their complete functions defined in the applicable FIPS or NIST recommendations. Now, originally, validation test suites, our philosophy was that the validation test suites are designed to test all specifications addressable at the algorithm level within a complete standard or a complete function within that standard. And the complete algorithm must be within a single cryptographic algorithm boundary. And this worked pretty well until technology advanced and computers got smaller and chips could get more stuff on them and everything else. And we realized then that it's not always the case where a whole algorithm's specification, the whole algorithm implementation is on the same, it is within the same boundary. And a good example of this are the PIV cards, where you have limited processing and limited memory, and you're going to have part of it on the card and part of it off of the card. So we had a philosophy update, and we said, you know, it's better to test something rather than nothing at all. So in 2011, we introduced component testing, and this provides assurance of an individual component of an algorithm when the complete algorithm or function isn't contained within a single boundary. One thing to note, we don't test mathematical functions, we test functions are part of a standard. Now I say that, but you can look in some standards and you can say, well, this function does this mathematical thing. We don't test the mathematical function. A good one is the exponential, you raise this to the power of this mod whatever, so the mod exp. But then you'll see that there are several functions defined that do just that, but they're used for different purposes. So we always test the components of a standard. Some examples. The ECDSA signature generation function has two steps. It hashes a message, and then it signs that hash. Now on the PIV card, the hashing of the message is done off the card, okay? But the signature of that hash is done on the card. So in order to create a component to test this ECDSA signature generation component, we find out the implementation you have, what size hashes does it support, and then we just test the signature generation component that's on the card by giving it hash length inputs and see what the signature looks like, okay? So, and in doing that, we know that the part of the ECDSA signature generation function on the card has been developed correctly. Here's a list of all of the algorithms and components we currently have validation testing for. And you can see it spans from symmetric algorithms, asymmetric algorithms, the modes of operation, which is the whole 38, special publication 838B series. And you have your hashing, your random number generator, your key agreement schemes, your KDFs, a whole assortment of things. And then down here in the corner we have the test, all of the component testing we currently have. And basically when we see a need for something, or somebody, and it could be any of you say, you know, we have a need for this, we evaluate it and we determine, do we need to have validation testing for that? Is that going to make things more secure? And yes, let's see, I'm not sure. Okay, so I have some examples now. So the CAVP, we just dumbly test all the components within an algorithm. We don't care how it's used, we don't care where it's going to be used. Okay, this is a component. All those things are done at other levels. Either it's at the module level or a level even higher than that, wherever the, whatever gets that module put into it. So again, we're just talking about the algorithm. And so at the module level then, that's where they would say, oh, we're testing something where the whole algorithm's not in one place, where they're going to make sure that they have all of the algorithm validation certificates or validations that make up the whole thing. And some examples that I have are a place where, well, let's say you have an implementation of the KAS, the Key Agreement Scheme from SP 856A, and if you all are familiar with that, 56A defined two key derivation functions to be used with the standard, and one was the, well, it doesn't matter what they were, okay. But it turns out there were other KDFs that were being used with the 56A Key Agreement Schemes. So what we had to do is create a component test which basically tested all of 56A up until the generation of the shared secret value, and stops there. So it makes sure that everything works correctly up to the shared secret value, the ZZ value. And then we have a separate component validation test for the TLS KDF in SP 800-135. And together, both those things together, says that everything's been tested for the 56A implementation that's going into some module, okay? And there's a second example there. where the ECDSA signature generation, you would need a SHA validation, and then you'd also have the component test for the ECDSA signature generation component. Okay? So, that was Chapter 1. Chapter 2. Chapter 2 is how does the testing development process work? So basically, in the CAVP, after an SP is published by the Cryptographic Technology Group, we look at that special pub, or that FIPS, and we identify everything that we can test, okay? What can we test at the algorithm level to make sure that this implementation has adhered to those specifications? So we look at the components and the functionality and the mathematical formulas. And then we develop a suite of validation tests, as many as it takes, to address all of these things. We identify the requirements. We develop the test metrics for testing the algorithm. We exercise all of the mathematical elements. And we make sure that everything works correctly, and if anything deviates, even just a little bit, that it will not pass the validation tests, because this would be detecting an implementation flaw. Once we've finalized the suite of tests, we document this in the validation system document. On our website, there's one document for each algorithm that we support, and it is a tool for the user to figure out describing the validation test suite and what they need to do in order to test their implementation. If there are any questions about our validation system document or things in the standard or how do you do whatever, we try to incorporate this into our CAVP frequently asked questions. And so if you ever have a question, that's a good place to always look first and see if we've already addressed that question. But if it hasn't, send emails to labs or to me, and that's a good way to get that information out there to the people, because I try then to add that to the FAQ so that it becomes available to everyone. And then on our website also is a validation list of all of the validated implementations of each of the algorithms or components. And this is all managed in a database in the CAVP where we generate these web pages periodically. I think it's once a week or something, so that you can see all the validated implementations of these. And then you can see the link between our lists and the cryptographic modules that have those algorithms in them. But we develop, currently we develop the database. Every time there's a new algorithm, we develop a new table which lists all the different things, not the right word, but all the things that it's been testing. So, for example, with AES, is it supporting encrypt state, decrypt state, which modes of operation, blah blah blah. Okay, so and on our web pages it says all of the things it's been tested for. Okay. So these validation test suites, what kind of tests are included in these things? Okay, so it's like Chapter 3. So we have known answer tests. These are designed to verify the components of an algorithm. So for like triple DES, you have S boxes and you have permutation tables and you have all this kind of stuff. You have plain text and you've got keys. And if one bit of any of those things is changed, does that make a difference in your output? Well, it should. And that's how the algorithm is written, that it should come up with a different answer. And so that's what these tests do. And it goes through, let's say, the plain text known answer test. It puts a 1 in all zeros. And see what output do you get. It puts a 0, 1 in all zeros. And see what output you get. And each one of those things, checking each one of the bits, should result, if all of the other components of that test stay the same, you should get a different answer for each one of those things. And this assures that you do. We have a multi-block message test. This test is designed to test the ability of an implementation to process multi-blocks of messages, which a lot of times there's a chaining of information. Is it chaining that information correct? There's been times when it just gets one block okay, but then the chaining is where there's a problem, and so that's where this is testing that. The Monte Carlo test is a pseudo-exhaustive test designed to exercise the entire implementation, and so it's usually going through 4 million iterations of something, and it's just saying, you know, hopefully we're going to find something wrong. You know, something in your it could be a buffer problem. It could be all kinds of problems like that will be detected, or we hope will be detected by the Monte Carlo test. We have positive testing. Positive testing, if you had an algorithm that did addition, I would give you 6 and 2, and you would return the answer, and you would return 8. And if that's the right answer, I'd say, yep, you're working right. If you return 9, I'll say, you know, there's something wrong with your implementation. You're not getting the right answer. But that's basically what positive testing is. Negative testing is where an implementation is validated against invalid input data. The goal of this test is to test the ability of an IUT to recognize valid and invalid values. It's usually used for the verification of like signatures or PQG values, something like that. And let me see if I can find my page. For I should have. For signature, okay. For the signature verification test for, let's say, DSA, this might be RSA. I make change, so I give sets of values, and I introduce errors. So on one set of values, I might change the public key, okay? So if I change the public key, everything else is, you know, if the public key wasn't changed, everything else should have said it passed, okay? Can you see that changed? If I change the public key, do you come up with true or false? It should pass or not pass. It should say it failed. I make a change in the message, a change in the signature. I change nothing. And then I also change like the format that the data is supposed to be in before it gets hashed. So that would be the IR format. And I usually mention this because I thought this was such a cool vulnerability that was discovered and that I could test for in the CAVP. But several years ago, so first of all, in the PKCS, probably was 1.5 implementation, you had to put the data into a certain format. And so you would have, I don't remember it all completely, but there's something, and then, so the whole thing had to be the size of your modulus, okay? And so you would then, inside this thing, you had a few codes, and you also had your hash, which had to be at the end of the string, and then there was a whole formula based on the size of the hash. So you take the mod minus the hash minus a few of these known values you get put different places, and then you had all the zeros, and you're supposed to have that many zeros before you have your hash. What turned out, some bad guys were not putting all the zeros, were moving the hash over, and then on the end they would put extraneous information that nobody knew to look for except for the bad guys, the other bad guys. Okay, so what was happening was people were doing the signature verification. Instead of figuring out how many zeros to look for, they would just say, well, let me just read. Okay, I know I'm supposed to get this code, I know I'm supposed to get this code, I'm supposed to get all these zeros, then I'm supposed to get an FF, and then I'm supposed to get the hash. So they would do this, they get over to the hash would read, the signature would verify, everything was great, but what they didn't realize is there was extra data here that they never looked for that the bad guys did look for, and it was a place to hide it. So when that vulnerability was discovered, it's like, well, let's have an additional test in this suite of tests that says everything should pass, but let's not make let's not put the right number of zeros. And if they say it passed, then we know they have this vulnerability in their implementation. So that's something that was caught by this. Some examples of test suites for just a couple of the algorithms. AES, we have known answer tests for these different parts of the algorithm, multi-block and Monte Carlo. You have, for RSA, key generation and signature generation, you have positive testing and signature verification, negative, like I just told you. And SHA-3, we have short message and selected long message. Again, these are basically positive testing, and then the Monte Carlo. Okay, so that's just food for thought, or whatever. You probably have seen this, or you know about it. This is the whole scheme of, what's the workflow? What's the flow of getting something validated, right? So a vendor selects a lab, submits an algorithm implementation for testing. The lab generates the algorithm test vectors using the CAVS tool, which is only released to the different laboratories. Then either the lab tests the algorithm implementation in-house, or the lab sends test vectors to the vendor to test. Once these are tested, the lab then verifies the results of the validation tests, because what the vendor does is, they have this sheet of, here's your input values, what do you get as output? Tell me the answers, right? They send that back. The CAVS tool then verifies that with the lab's help, and the algorithm test report is then sent to the CAVP for review to assure that everything has passed correctly. Let's see. We review it. We accept or reject it, and then we put it out there. And there's our web page right there, so you can go see everything else there is to know about the CAVP. Okay. Some test suites in progress. I showed you all of the algorithms that we currently have validation testing for. These are a few that are in the works. So 56C, which is being added to 56A. 132, and then adding SHA-3 to all of these existing algorithms. Here's the future algorithm testing. So again, these are things that have already been published that we need to have validation testing for. So again, they're on my to-do list. And you can see some of them are new revisions of a document, so be changes to the existing testing. Here's your 90B and 90C. Just to give you an our status for FY16. We've got lots of good stuff going on, and just to show you here our progress by fiscal year. Business is good, and we contribute the good business to more programs using the CAVP, or the validated algorithms, in their programs, like NIAP is using it now. So that's it. Here's numbers to go along with all those things. And any questions? Yes?
I'll say this loud so we don't have to repeat the question.
Okay.
And I caveat this by saying I was put up to this question by somebody in marketing/competitive intelligence.
Okay.
If I discover a CAVP cert from a competitor, where the OE data is blatantly wrong, I will not use the word misleading, even though I mentioned it, can I bring this to your attention for remediation?
You can, and we'll deal with it. Okay, but I believe that the labs, we put guidance out there on what kind of information we expect to have out there for the OEs. Okay, that's in the FAQ, and we don't know if it's right or wrong, because the labs and the vendor are the ones that are, working on this module validation, this algorithm validation, okay? The laboratories should be assuring that the information on this OE, what it's being tested on, is accurate, and is accurate with the vendor and the lab, and with the documentation we send out for guidance on how to make that stuff, you know, clear and correct. And bring it to our attention, and then we will hopefully educate people how to do it correctly. Okay? Yes?
You mentioned in one of your slides that when the cryptographic algorithm is not run within a single node boundaries, like ECDSA, for instance, the vendor has to supply two certificates, one for the hashing and one for the
part.
Computation. How would that work in a PID card environment where the vendor supplies just the card and is not responsible for the application or the PC application or whatever application scoring the signature function from the card, because we don't control the hashing algorithm, so we cannot provide that.
Right. So you're saying as a vendor, if you develop the PIV card and you have just the one part of an algorithm on the card, how can you do how can you test for the other part when you don't know where it's coming from? You know, the hashing, you're not in control of that. But with your algorithm implementation, you only have the component, okay? So that's all, and you get put onto the component validation list as, you know, this is a PIV card, and it does the signature generation component test correctly, okay? When it goes to another level, so like the module level or wherever, if somebody picks up your piece in the module, then they must know what the other part is. And so at a different level, where it's actually pairing it with wherever that hash algorithm is, that's where that hash algorithm has to have an entry on the hash validation list by somebody else, and those two things can be put together then at a higher level. Okay?
Let's thank Karen for her talk. Okay, never mind. Caroline. Caroline. So your talk is supposed to have 35 minutes long?
It's not going to be that long.
Okay, so if I cut it to 30 minutes, will be okay to catch up with the lunch break, and I will give you 5 minutes remaining reminder